Alright, welcome to another part of the Wild Networking series where I focus on network engineering as you would see it more in the wild versus as you would see it on like a certification exam or in a classroom. So we've been focusing on RFCs because RFCs are available just if you have a public internet connection. There's no special requirement to access RFCs. You just Google for RFC and then you can say BGP and yep, it's the first one. And if that doesn't take you right to it, you right to the one you wanted to see. Say you wanted to see a update RFC like on the subcodes, then they're going to be listed up here. You can see what the prior version of it was under obsoletes, and then you can see well, first of all, the errata, that's important too. That means that there's a mistake in the RFC that has been identified and corrected. So that's of course important. It looks like the mistake is oh, so the mistake is it looks like they weren't clear that when the hold timer expires, the routes all get deleted instantly. Yeah, so that's another thing that's important to be aware of if there's errata, being clear about that and knowing that there is a mistake in there. The other thing I think is important to know in RFCs is the category. So this is a standards track. It's a really essential RFC to know about. One of the things I would like to do as well is make a series on internet standards. And internet standards are, I believe, all listed in one place somewhere. Let me try to find that. RFC Internet Standards. So okay, I guess I can do it on the, here's an RFC search page, so maybe if I search for standard, or just go to additional criteria. Here we go. So now I can go to standards track, internet standard, and that's something I might consider doing in the future. Is well, is RFC an internet, RFC1 an internet standard? No, it's an unknown. I'm surprised that's showing up because it's looks like it's an unknown. It's not an internet standard. It's unknown. So I'm really surprised to see that in there when I specifically said just to show me. Okay, it looks like any got selected again. So we'll see if I can. Okay, here we go. So now I narrowed it down to 120 results. Looks like the first internet standard we got is RFC 20, and that makes more sense. ASCII is familiar to me. It's definitely an internet standard. So let's go to the HTML with inline errata. That sounds good. Now this is a really old RFC, so it's going to look a bit different, but yeah, so we can see here's the RFC for ASCII format, and it's an internet standard. So one thing I would like to do eventually is just go through all of the standards track RFCs, because that's really going to give me a really solid understand, like basically any gaps in my knowledge, which I'm sure there are some. Well, I'm sure there are quite a few. This will absolutely fill in. And there's some like PPP, you know, I probably don't need to learn about that. Post office protocol, I probably don't need to. Oh, I think that's the POP. Okay, that's the POP protocol. I think that's. But just, you know, even if it's not relevant, just going in and seeing what it says, because these are definitely, you know, these are internet standards. So if my job is to work on the internet, which it is in a large sense, I need to be familiar with the standards, even if they're standards that I don't directly work with day to day. Okay, so that's a different series. Probably call that the standards track series. So I'm kind of getting off topic. I'm going to do right now I'm focusing on doing a part 3 to this wild networking series on BGP. So last video I finished learning about the update message format. So the next message format is the keep alive message format. And one thing I did in my lab is I set up a new device here. This I think it's just a Debian Linux VM. So let's take a look at that. Yeah, so I can do a uname-a. Okay, so it's actually in Ubuntu, which is good. I actually am more familiar with Ubuntu. That's what this lab is running on. An R610 Dell PowerEdge running Ubuntu server. So this is the same. Ubuntu server is not an actual thing. It's just Ubuntu with things installed. It's like getting Windows, but you have, you know, like a Minecraft installed on it. It's kind of the same thing. Like Ubuntu server is different from Ubuntu Home because it has different things installed on it. It's almost like, you know, Windows Professional versus Windows Office or Enterprise or whatever. So yeah, this is just Ubuntu Linux. That's the only really relevant thing. Anything else into Ubuntu server, Ubuntu Home, is just what's installed on it by default. But Ubuntu server on my Dell PowerEdge has been just a lifesaver. Everything runs a lot better. Everything's actually easier to use. So I'm really happy with Ubuntu server. So yeah. So now I'm automating, or I've got a VM here, which is just a Ubuntu command line. So if I switch to the root, you'll see all the familiar Linux commands. But the reason I have this is because of a tool called Scapy, S-C-A-P-Y. So if we're talking about network engineering as you see in the wild, we got to be talking about Scapy, because you can use this tool here to toggle bits in a packet, craft your custom traffic, and send it out in the wild. So if you're going to be doing network engineering in the wild, and you're really familiar with a tool like Scapy, you know, that's just like having turbocharged engine in your car. You know, if you don't know about Scapy, like, yeah, you can get to point A and point B, but if you've got a lot of knowledge about this tool, you can do so in a lot more interesting, robust ways. So this is definitely going to be an important part of this series going forward, learning how to use SCATB in a more advanced way. Right now I have some familiarity with it, but it's definitely not one of my strong points right now. So one thing I would like to do with it, which I think would be interesting, is to craft a packet that has the bit we were looking at in the last video toggled on. So right now there's a bit in BGP that tells you the AS. Well, there's a field in the BGP portion of the TCP data that tells you the autonomous system path, and this only shows up when you're exchanging network layer reachability information. Right now we're not doing that. We just got a keep alive message, but I can force that to happen by bouncing an interface. So I'm going to do that on R6. And I'm going to bounce the so hello 0.0 disable. Okay, so now we'll get an update message. It will be for withdrawing a route. So it won't have any network layer reachability information yet because we're just withdrawing the routes. There we go. So we don't see any of that NRI. We don't see any path attributes. So let's roll that back, and then we'll get some path attributes, and we can open up the AS path attribute. Okay, so here's our update message. So we'll open up the path attributes and the so let's open up the AS path attribute. So I was expecting to see inside this in these flags here, I believe, this field here, this origin, or in some way a part of this data here. I was expecting to see what's in the origin. That was incorrect. My understanding was incorrect. This is actually its own field, this origin. Now origin, from what I understand, is always in a modern network going to be IGP, because your only other options are EGP, which is a special legacy protocol related to, it's called Exterior Gateway Protocol, and that was replaced by BGP. So as long as we're running BGP version 4, which we definitely are, if we go to, and I think this marker is what indicates that. So then we will not be running EGP. That is a different protocol. It's a legacy protocol that is no longer used in modern networks. The other option we do have, though, is setting this, because this is 2 octets. Well, actually, it's quite a bit. Well, the actual code here, the origin code here. Oh, yeah, okay, well. Okay, the origin code here is actually 1 full octet, which is 8 bits. So, but from what I understand, only the first 2 bits are relevant, and even then you only need to represent a max value of 3. So you would do that with the last 2 bits on. So yeah, you only need the 2 bits, and then the maximum value you can represent is 3, which gives you a total of 4 values, because 0 is a value as well. But you only need 3 of those 4 values because you have the IGP origin, the EGP, which, as I said, is never available, and then you have the third type, which is the unknown, which you, I think you might be able to see it at some point. But here we have the IGP. Now what I'd like to do is craft a custom packet with this flipped to EGP, as a learning exercise for Scapy. So let's try to do that. I'm going to type in Scapy, and maybe there's some. Okay, so here's the documentation for Scapy. So yeah, so let's go to starting Scapy. Well, let's actually go to simple one-liners. So okay, so we can use Scapy the same way you would use Nmap. But I'm looking for, but it has additional capacity, I think, unless you can do this with Nmap. I'm sure you can. But it's basically like Nmap, except for as a Python library. But this is perhaps one of my favorite uses for it, is just wireless sniffing. When I have used it, I haven't used it that much. Okay, I guess I'd rather. I think this is going to be too advanced. Doing that, that's just going to be really difficult. So, I think I would rather, besides doing that, just go through this tutorial. But actually, what I'd really like to do is keep reading that RFC. Keep working on that, because this is meant to be about BGP. So let's do that. We're going to keep working on the RFC. Hopefully get to a major break, or at the very least just some of it out of the way, because we're not even at the 1/4 mark. We're almost there, it looks like, but definitely not at the 1/3 mark. So we just got to keep plugging away on this. So let's keep working on this BGP RFC, and then put in the description to go through this this tutorial here, this interactive tutorial. Oh, we got recipes here. Okay. Yep, and then yeah, so that's the plan. Okay, so this is section 4.4, keep alive message format. BGP does not use any TCP-based keep alive mechanism to determine if peers are reachable. Instead, keep alive messages are exchanged between peers often enough not to cause the hold timer to expire. A reasonable maximum time between keep alive messages would be 1/3 of the hold time interval. Keep alive messages must not be sent more frequently than 1 per second. An implementation may adjust the rate at which it sends keep alive messages as a function of the hold time interval. If the negotiated hold time interval is 0, then periodic keep alive messages must not be sent. A keep alive message consists of only the message header and has a length of 19 octets. So let's verify that. Here we have a keep alive message. So let's see. Yep. So the header consists of the marker, the length, and the type. We can see the length is 19. Let's take a look at how often they are being sent. So we'll filter it out, and we're going to filter out based on the message type. So we can do apply as filter the selected attributes. So we've got bgp.type equals 4. You can see that here. And now let's also filter out just on one side so we can see how often they're being sent. So we're going to go to the packet here, and then we're going to go to the source, and then we're going to apply as a filter the AND selected. There we go, and now we're filtering out based on those two criteria. We've just narrowed it down to the keep alives from the .2 router. Okay, and looking at the timestamps, let's go to the beginning. Okay, so it looks like every 25, 30 seconds or so, we've got keep alive messages being sent. Alright, section 4.5 is the notification message format. A notification message is sent when an error condition is detected. The BGP connection is closed immediately after it is sent. In addition to the fixed size BGP header, the notification message contains the following fields: error code, error subcode, and data, which is a variable field. It doesn't have to be a particular length. Error code. This 1 octet unsigned integer indicates the type of notification. The following error codes have been defined. So we've seen the cease multiple times. That's the one I think we're familiar with. So error code 1 is the message header error. Error code 2 is the open message error. Error 3 is the update message error. Error 4 is the hold timer expired error. Error 5 is the infinite state machine error. And error 6 is the cease error. So I would like to try to trigger each of these errors. The first error is the... Oh, okay. So it looks like we're having an explanation here about the error subcode. This 1 octet unsigned integer provides more specific information about the nature of the reported error. Each error code may have one or more error subcodes associated with it. If no appropriate error subcode is defined, then a 0 unspecific value is used for the error subcode field. Okay, so here's the first type of error that I would like to try to trigger. So this will occur, number 1, if the connection is not synchronized, number 2, if there is a bad message length, or number 3, if there is a bad message type. So this is where I can use Scapy. I can craft a custom packet and send it to a device, and it could have one of these 3 errors, and then I can send it with a bad message length or a bad message type, and then I will receive a notification error back. That's what I'll get. I need to pause the video. I'll be back shortly. I'm actually getting a bit too tired to have an extended video today, but I'll do what I can.
Okay, welcome back. Sorry, I took a break. It's actually the next day, but I did want to finish, or kind of finish the thought I had, I think, which was starting to integrate Scapy more into all of this. But for now, I am going to focus more on the RFC. So we already finished the keep alive message format section in the last video, so the next part is the notification message format. A notification message is sent when an error condition is detected. The BGP connection is closed immediately after it is sent. Okay, and I remember we actually got through here as well, and kind of what I was hoping to do is get each of these messages, and that's why I kind of went on that tangent to talk about Scapy, because Scapy is going to be the easiest way to see those messages, just to craft a packet that has a error in the message header, that has or any of these headers, and see the response a device will send after receiving that. So one thing I can do to look at this traffic is I can do like a man in the middle architecture here. So we've got my network automation machine. I'm going to need at least one more port on it. So let's see here. So I've got Right now I've only got one adapter, so I'm going to need another one. Okay, so I've got two adapters on there now. So one adapter is going to go into the hub. Oops. It didn't. Oh, maybe I didn't hit apply, I only hit OK. Okay, there we go. Yeah, I didn't hit apply. Oh, but we got a. Okay, so it seems to be working now. There might be a problem with it having been up for so long. Okay, yeah, it looks like it. So I'm going to give the whole thing a reboot. It only takes 5 minutes now that I've reinstalled now that I've changed the operating system from ESXi to Ubuntu server. It doesn't take that long to reboot. Okay, so hopefully I can get connectivity here. It looks like it's thinking. In the meantime, let's keep reading the RFC. In addition to the fixed size BGP header, the notification message contains the following fields: error code, error subcode data. I believe we looked at that. So actually, I'm not sure, but okay, it looks like this is ready to go now. So sorry, I'm so scattered-brained here, but I want to make sure that I'm integrating Scapy into these videos because I really want to learn that tool, and it's really relevant to real-world networking, which is what this series is all about. So yeah, instead of these two devices being directly connected to each other, now I'm going to have the devices connect into a hub, and then the hub is going to be connecting into this device here. So it's like a man-in-the-middle attack. It's like I found a way to, and this is something you could do in the wild, in the real networking attack. Don't do it, but especially if you're really good with cabling. If you find a Cat6 cable, you can, and you're really good at cabling techniques. I'm not. I've done like hardly any layer 1, but you can snip it in two, then reform the connections on each side, plug them into a hub, and then plug that hub into PC just like we're seeing here. So this right here is, even though it's in my lab, is a wild networking scenario that please don't do. Or yeah, I am not recommending anyone do that. I should probably be more clear about disclaimers on this channel, but this here is a thing you could do out in the wild, but it would be, I think in all cases except for your own personal lab, a crime. So please do not do this. Okay, so yeah, let's just test the connectivity. Oops. For some reason it's not. I'm not getting. Oop. Oh, somebody's opening the garage door. Oh. Okay, here we go. So I'm gonna test that. I can still ping the other side. It looks like I can't. Oh, there's no descriptions. Okay, so there's clearly something going on here. Yeah, so it's meant to be in 0 and 0, so let's make sure that that is the case. Yep. Yeah. Okay, so it is in 0 and 0. ETH2 maps to GE000 in my lab. I'm sure there's a way to relabel it, but it's kind of a lot to figure out right now. So, so for some reason those ports aren't coming up. Oops. Yeah, I'm not sure what's going on with that port. Oh, you know what? I think what's going on is the show chassis FPC 0. I think it's still in testing mode, so it's not quite, even though it's rebooted, it's not quite ready for use all the way yet. Even though I can get to the CLI, that doesn't necessarily mean that I have full functionality. Okay, so I'll have that soon enough. In the meantime, I'll keep reading this. Error subcode, this 1-octet unsigned integer, provides more specific information about the nature of the reported error. Each error code may have one or more error subcodes associated with it. If no appropriate error subcode is defined, then a 0 unspecified value is used for the error subcode field. Message header error subcodes. Connection not synchronized, bad message length, bad message type. Open message error subcodes. Number 1, unsupported version number. Number 2, bad peer AS. Number 3, bad BGP identifier. So here's some errors that we can very easily create. We can make a bad AS for the peer, and we can use a bad BGP identifier. The 4th one is unsupported optional parameter. The 5th is deprecated, so that's just not going to be used. The 6th is unacceptable hold time. That's another one that I think would be easy to create. So this here, message header error subcodes, connection not synchronized, bad message length, bad message type. I think those are going to be more difficult to create, but I think I could make each of these using Scapy. Okay, so the update message error subcodes are: number 1, malformed attribute list. Number 2, unrecognized well-known attribute. Number 3, missing well-known attribute. Number 4, attribute flags error. Number 5, attribute length error. Number 6, invalid origin attributes. Now, with the origin field, what I remember reading is that there's only 3 types of origins represented with the values 0, 1, and 2. So even the amount of bits you need to represent those values, you need 2 bits, you still have an extra setting of 1, 1 in those bits, which maps to 3, which is the 4th option. Since we don't have a 4th option, we only have 3 options, we have that extra bit. Or, well, we don't have an extra bit, we have an extra unused settings within those 2 bits. In addition to that, from looking at the Wireshark capture, it appeared as though the origin field was 1 full octet long. So we've got an extra setting from our 2 bits used for the origin field, as well as 6 additional bits. So that's a lot of information you can use in that field. So I bring that up because I am curious if there's some sort of BGP extension or something that uses those extra unused bits that were meant for the origin attribute. Or if there's something interesting I could do in Scapy by using those bits. Because as long as I only toggle the from left to right first 6 and leave those last 2 alone, I won't be No, actually, never mind. I can't toggle those bits because then I'll get, if I turn one of those on, I'll have a unrecognized origin code. So yeah, because the origin code is created by the settings of all 8 of those bits, so I would have to, if I modified those bits, be sure that the routers could interpret that origin attribute still, and unfortunately I don't think they can unless it's 0, 1, or 2. So okay, so much for that idea. I kind of was curious about that, but it just sounds like that's not feasible. Is playing around with those bits. All right, so the 8th update message error subcode is invalid next hop attribute. That's I think an easy one to try to do in the lab. The 9th is optional attribute error. The 10th is invalid network field. 11th is malformed AS path. Data. This variable length field is used to diagnose the reason for the notification. The contents of the data field depend on the error code and error subcode. See section 6 for more details. Note that the length of the data field can be determined from the message length field by the formula message length equals 21 plus data length. The minimum length of the notification message is 21 octets, including message header. Okay, so I'd like to get a notification. Okay, and now I've got I got my capture still going from the last time. So this is a dead capture. Yeah, we can see we've had number 109, but nothing since that. So I will close this. This is just leftover from the last time. Now with a hub, all of the traffic is sent out of all of the ports. So it might seem unusual to sniff this connection here by sniffing this port, but this is the only way. Well, actually, I could sniff either of these ports because, as I said, all traffic is forwarded out all of the ports, so I would see it back and forth regardless of when I sniffed. But I'm just going to sniff this one to prove a point that hubs work in that manner. Okay, so I've got my FPCs working fine, and yep, we can see, sure enough, even though intuitively you would see this and think it's not going to go over this link because it appears as though it would just go like this. This is a hub, so it sends it out all of its ports, so it goes over here as well. And the reply goes over there as well. It just goes everywhere. Now, is this traffic going to get received and processed by anything? No, it's not, because it's just going to go to this jump host. Jump host says, I don't know what you're talking about. I'm not, I don't have this destination IP. I don't have this destination MAC. What are you talking about? And it just throws it away in the garbage can. So that's why switches are so much better, because you don't get the extra traffic going to places where it doesn't belong, so you can conserve bandwidth. And then, of course, security is a big thing too. Here we're showing an insecure situation, and this is made easier by having this hub series. So let's just say this was a part of the topology. Now in my scenario where you please don't clip a wire and put in a hub like this, if they already have a hub out there, you just plug into the hub if you can get access to it, which again, please do not do. But the thing is, if they're using a switch instead of a hub, and and they have a good network engineer. If you plug into one of the ports on the switch, the traffic will still be protected. But that's not true with a hub. Okay, so I think I read. I'll read these again. So number 8 is invalid next hop attribute. Number 9 is optional attribute error. Number 10. Oh, no, okay, yeah. So I read all the way through here. So before reading about path attributes, I want to see a notification message. Okay, so to see a notification message, one thing I could do is just shut down one of the ports. Okay, so now I'll get a notification, I believe. I think so. I might not actually because it's just shut down. I'll get one after the whole timer expires, I think. I'm a little bit uncertain whether or not I'll get one. I kind of think I think I'll get one after the whole timer. Oh, you know what? See, it's because the whole link is down. I should have just shut down like the sub interface and left the link up. Yeah. So, yeah, I don't get a notification message because... Oh, no, I do. Yeah, the whole timer expired. So, yeah, I was right. Okay. So, here's our notifications. Yep, whole timer expired. That's the notification that I would get. So, I was right. I know my stuff in this regard. But it's always good to have a review and confirmation to actually see it happen. Okay, I need to take a quick break. On that high note, I'll be back shortly. All right, welcome back. We were looking at the notification message for a expired full timer. So here it is, full timer expired. Okay. All right. Well, I don't see. I thought there was like something about the whole timer. Oh, here we go. Yeah. So this should be error code 4 in the notification message. So we're gonna have. So we have the regular BGP marker length and type. Marker length and type, but this is type 3, which is a notification message, so we'll have an error code, error subcode, and data. So here's our error code, here's our subcode, minor error code, and then we don't have any data, but it's a variable field. It can be 0, which is it is in this case. But our error code is type 3, or sorry, it's type 4, which is whole timer expired, because the whole timer expired. Alright, so section 5 is path attributes. This section discusses the path attributes of the update message. Path attributes fall into 4 separate categories. Number 1, well-known mandatory, which are, number 2, well-known discretionary. Number 3, optional transitive. Number 4, optional non-transitive. BGP implementations must recognize all well-known attributes. Some of these attributes are mandatory and must be included in every update message that contains NLRI, network layer reachability information. Others are discretionary and may or may not be sent in a particular update message. Once a BGP peer has updated any well-known attributes, it must pass those attributes to its peers in any updates it transmits. In addition to well-known attributes, each path may contain one or more optional attributes. It is not required or expected that all BGP implementations support all optional attributes. The handling of an unrecognized optional attribute is determined by the setting of the transitive bit in the attributes flag octet. Paths with unrecognized transitive optional attributes should be accepted. If a path with an unrecognized transitive optional attribute is accepted and passed to other BGP peers, then the unrecognized transitive optional attribute of that path must be passed, along with the path to other BGP peers with the partial bit in the transitive flags octet set to 1. If a path with a recognized transitive optional attribute is accepted and passed along to other BGP peers, and the partial bit in the attribute flags octet is set to 1 by some previous AS, it must not be set back to 0 by the current AS. Unrecognized non-transitive additional attributes must be quietly ignored and not passed along to other BGP peers. New transitive optional attributes may be attached to the path by the originator or by any other BGP speaker in the path. If they are not attached by the originator, the partial bit in the attribute flags octet is set to 1. The rules for attaching new non-transitive optional attributes will depend on the nature of the specific attribute. The documentation of each new non-transitive optional attribute will be expected to include such rules. All description of the multi-exit discriminator attribute gives an example, and you can see I misread this V for all because I blurred the two lines together, but this says the description of the multi-exit discriminator attribute gives an example. All optional attributes, both transitive and non-transitive, may be updated, if appropriate, by BGP speakers in the path. The sender of an update message should order path attributes within the update message in ascending order of attribute type. The receiver of an update message must be prepared to handle path attributes within update messages that are out of order. The same attribute with the same type cannot appear more than once within the path attributes field of a particular update message. The mandatory category refers to an attribute that must be present in both iBGP and eBGP exchanges if NLRI are contained in the update message. Attributes classified as optional for the purpose of the protocol extension mechanism may be purely discretionary, required, or disallowed in certain contexts. So I'm not sure what the difference is between purely discretionary and discretionary. I don't see any purely discretionary. I only see discretionary and mandatory, which I'm guessing is the same as required. I don't see any disallowed. But here's a table. We've got the origin attributes, which is mandatory for both eBGP and iBGP. We've got AS path, which is also mandatory for eBGP and iBGP. Next hop is also mandatory, and that's what we see. And so if I bring this back up, that roll back, now we'll get the update message that we just read about, and we'll see the AS path. Yep. So. Nope, I gotta scroll over. Okay, yep, so here's an update message here. And oops, this is a withdraw though. We need one to here we go. So here's the path attributes, and sure enough, all three mandatory attributes, origin, AS path, and next hop, are present in this update. They have to be, otherwise it's not a valid update message. Now they can have more than that. They can also have the multi-exit discriminatory, which is a discretionary attribute for both eBGP and iBGP. They can have the local preference, which is looks like it has special directions for eBGP, but is required for iBGP. You can also have the atomic aggregates, which it looks like there's special instructions for both eBGP and iBGP on that. And then the final one is the aggregator, and that's discretionary for both eBGP and iBGP, just like the multi-exit discriminator was. But in my experience, the most significant ones are not even the origin. That's really not all that significant, because it's going to be an IGP origin. The only alternative to that is eGP, which is just a old school protocol that is just not going to originate from in modern networks. But the two big ones are the AS path and the next hop. The AS path can be used to make decisions on which AS you want to send it to. It can be used to accept routes, to reject routes, to modify routes. This is a key attribute in BGP, and a lot of the configuration to manipulate BGP traffic will be given to this AS path attribute. And the next one is more self-explanatory than that. It's just the next hop. This one is also a big one. A lot of policies set the next hop self. That's a really common BGP policy included in a lot of places, because BGP is quite a bit different than OSPF or other such protocols, as I've discussed before, because you're not exchanging actual routes, you're just exchanging network layer reachability information. You're exchanging data. I mean, it's literally just TCP payload. A payload. It's just the data portion of the TCP packet is all it is, and then it has its marker in it, and now you can see what's in there. And what I'm talking about is this network layer reachability information. This isn't an actual, I mean, it is an actual IP route. You can see there's 32 bits, and it's describing a IP route, but it's not the same sort of thing as like OSPF link state information or like route exchanging the databases or something like that. So one difference is that it doesn't automatically know what the correct next hop to use is. If it were from BGP or EIGRP or something like that, because it is a valid route, or because it is exchanged more kind of as an IP and less as kind of just data in a TCP payload, it knows what the next hop is. Like, it makes sense in the context of IP addressing. So things like the next hop really aren't going to go awry in the same way as it will with BGP, where it's not seen in that context, it's just seen as data. So you've got to make sure that your path attribute next hop makes sense, because you can put anything in there and it will be accepted by the BGP protocol and sent on. It won't be interpreted by the other side, but you can send more custom things using BGP than you can in other protocols, because you're exchanging data and not not actual routes. Okay, so section 5.1 is the path attribute usage. The usage of each BGP path attribute is described in the following clauses. So the origin path attribute. Origin is a well-known mandatory attribute. The origin attribute is generated by the speaker that originates the associated routing information. Its value should not be changed by any speaker. I wish they said more about that, but I think I've got a good grasp on that. It's just always going to be set to, I believe it is 0, and you're not going to see, you might see a 3, or sorry, a 2. Okay, no, yeah, so it's a 0, but you're only going to see 2 other values, and the second value, EGP, you're just not going to see in modern networks, and the third value, unknown. I don't think you'll see either, unless you use like a custom packet crafter. And then of course, if we use a custom packet crafter, and let's say we set it to value of 4, we're gonna get a notification message back once we send that. Okay, so the next path attribute is the AS path. AS path is a well-known mandatory attribute. This attribute identifies the autonomous systems through which routing information carried in this update message has passed. The components of this list can be set under AS set or AS sequences. When a BGP speaker propagates a route it learned from another BGP speaker's update message, it modifies the route's AS path attribute based on the location of the BGP speaker to which the route will be sent. When a given BGP speaker advertises the route to an internal peer, the advertising speaker shall not modify the AS path attribute associated with the route. B. When a given BGP speaker advertises the route to an external peer, the advertising speaker updates the AS path attribute as follows. Okay, so if it's a EGP, you're passing it between the same ASs. The AS path is not going to get modified, and of course, why would it? It's not a modified thing. It's the same value. But when you pass it between different values, it does get modified, and it gets modified as follows. Number 1. The first path segment of the AS path is of type AS_sequence. The local system prepends its own AS number as the last element of the sequence. Put it in the leftmost position with respect to the position of octets in the protocol message. Thank you for saying that, by the way, because that has not always been clear. Okay. If the act of prepending will cause an overflow in the AS path segment, i.e. more than 225 ASs, it should prepend a new segment of type AS sequence and prepend its own AS number to this new segment. Okay, so it looks like we've got segment types and two types. We've got AS path and AS sequence. Let's see what we've got here. So we've got AS path is the type, but it looks like we could also have AS sequence if there were more than 225, if the length of this sequence is more than 225. And we can see right now the length of this sequence is just one. And it is one because we have, I believe, an eBGP connection. Let me check that. Okay, yeah, so we can see, let me make this a little bit easier to read, that the AS here is 400, but the peer is 400, the local is 600. So sure enough, it is a eBGP connection. But it's only got a single entry in the AS path. So for it to turn into an AS sequence, it would need to have 255. And I wish I could trigger that somehow, but I'm not sure how. Number 2, if the first path segment of the AS path is of type AS_set, the local system prepends a new path segment of type AS sequence to the AS path, including its own AS number in that segment. Number 3, if the AS path is empty, the local system creates a path segment of type AS sequence, places its own AS into that segment, and places that segment into the AS path. When a BGP speaker originates a route, then the originating speaker includes its own AS number in a path segment of type AS sequence in the AS path attribute of all update messages sent to an external peer. In this case, the AS number of the originating speaker's autonomous system will be the only entry in the path segment, and this path segment will be the only segment in the AS path attribute. B, the originating speaker includes an empty AS path attribute in all update messages sent to internal peers. An empty AS path attribute is one whose length field contains the value 0. Whenever the modification of the AS path attribute calls for including or prepending the AS number of the local system may include/prepend more than one instance of its own AS number in the AS path attribute. This is controlled via local configuration. Okay, yeah, so I'm not sure how to get it to have more than 225 list entries in its AS path. Maybe I can like form a loop and like allow there to be a loop. I know you can do that. So you can do set and then loop or something. I don't know what it would be. Maybe it's under the neighbor. Yeah, I thought there was like a command to allow for loops. It was like set loops or something. not see it. Yeah, unfortunately, I do not see the command I was thinking about. Okay. Alright, so let's just continue on. It's kind of going over my head in some ways, but I think that's okay. Like, I can't even remember if I read this part or not. I'm pretty sure I did. Yeah, I read to here. Okay, so the next attribute is the next hop attribute. The next hop is a well-known mandatory attribute that defines the IP address of the router that should be used as the next hop to the destinations listed in the update message. The next hop attribute is calculated as follows. Number 1, when sending a message to an internal peer, if the route is not locally originated, the BGP speaker should not modify the next hop attribute unless it has been explicitly configured to announce its own IP address as the next hop. When announcing a locally originated route to an internal peer, the BGP speaker should use the interface address of the router through which the announced network is reachable for the speaker as the next hop. If the route is directly connected to the speaker, or if the interface address of the router through which the announced network is reachable for the speaker is the internal peer's address, then the BGP speaker should use its own IP address for the next hop attribute, the address of the interface that is used to reach the peer. Number 2, when sending a message to an external peer X and the peer is one IP hop away from the speaker, if the route being announced was learned from an internal peer or is locally originated, the BGP speaker can use an interface address of the internal peer router or the internal router through which the announced attribute is reachable for the speaker for the next hop attribute, provided that peer X shares a common subnet with this address. This is a form of third-party next hop attribute. Okay, I don't know what that means. Otherwise, if the route being announced was learned from an external peer, the speaker can use an IP address of any adjacent router known from the received next hop attribute that the speaker itself uses for local route calculation in the next hop attribute, provided that peer X shares a common subnet with this address. This is a second form of third-party next hop attribute. Otherwise, if the external peer to which the route is being advertised shares a common subnet with one of the interfaces of the announcing BGP speaker, the speaker may use the next hop address associated with such an interface in the next hop attribute. This is known as a first-party next hop attribute. By default, if none of the above conditions apply, the BGP speaker should use the IP address of the interface that the speaker uses to establish the BGP connection to peer X in the next hop attribute. When sending a message to an external peer X and the peer is multiple IP hops away from the speaker, aka multi-hop BGP, the speaker may be configured to propagate the next hop attribute. In this case, when advertising a route that the speaker learned from one of its peers, the next hop attribute of the advertised route is exactly the same as the next hop attribute of the learned route. The speaker does not modify the next hop attribute. By default, the BGP speaker should use the IP address of the interface that the speaker uses in the next hop attribute to establish the BGP connection to peer X. Normally, the next hop attribute is chosen such that the shortest available path will be taken. A BGP speaker must be able to support the disabling advertisement of third-party next hop attributes in order to handle imperfectly bridged media. A route originated by a BGP speaker shall not be advertised to a speaker using an address of that peer as next hop. The BGP speaker shall not install a route with itself as the next hop. The next hop attribute is used by the BGP speaker to determine the actual outbound interface and intermediate next hop address that should be used to forward transit packets to the associated destinations. The immediate next hop address is determined by performing a recursive route lookup operation for the IP address in the next hop attribute using the contents of the routing table, selecting one entry if multiple entries of equal cost exist. The routing table entry that resolves the IP address in the next hop attribute will always specify the outbound interface. If the entry specifies an attached subnet but does not specify a next hop address, then the address in the next hop attribute should be used as the immediate next hop address. If the entry also specifies the next hop address, this address should be used as the immediate next hop address for packet forwarding. Okay, so I'm kind of fading fast here. So I'm gonna save this as the next thing to go through, and I wanna be really fresh when I go through this, because the multi-exit discriminator is something I'm really not comfortable with. I'm more comfortable with the next hop attribute and the AS path attribute. That's for this video. We're at an hour and 12 minutes. I haven't put that much time in today, but I want to end this video, keep it manageable, and then, but what I want to end it with is the interactive tutorial for Scapy. So hopefully that won't take too long, but just straight up following a tutorial I find not quite as intensive as reading and understanding an RFC. So okay, so we're gonna start by doing we're gonna just do this whole tutorial and then end the video. Okay, so sudo Scapy. Oh, I have admin privileges. Okay, so it looks like okay, it's rendering colors. Well, let's take a look at that. Okay, this would actually change it though. Okay. Okay, I don't mind what's the black and white? I might like that. Okay. I like the green one better. The yellow and green. I mean, this looks fine. Let's go with this, the bright theme. Okay, so other parameters such as config.prompt can also provide some customization. Note Scapy will update the shell automatically as soon as the comp values are changed. Okay, it looks like it has to run on Python 2, unfortunately. I'm curious about that. Yeah, looks like other people are as well. It pops up right away. Oh, okay. It looks like it does have it for Python 3. I don't think I have Python 3 on this. Oh, I do have Python 3 on that. Okay, so let's do Python 3-n. Okay. Yeah, I'd rather always be focusing on Python 3. Okay, so that's going to be version 244. So I guess I'm curious. Is this on? Can I do like a loud version? Like well, let's do this. Yep. So this is Python 3. I got that from that message there. Okay, perfect. Okay, good. That's what I want. All right. So first steps. Let's build a packet and play with it. So we're going to do is that a dash or no? That's an equal sign. IP TTL equals 10. Okay, so here we've got a packet. This should look a little bit familiar here because we've got packets here as well. So let's look at a TCP packet here, just like that, and which should look because a packet is the addressing header. We're not building a frame, so it should look familiar to what we have here. So, yep, so we've got an IP packet with nothing in it. So let's add some stuff to it. Okay, so we're going to add a source address to our IP packets. And it'll be... Oh, actually we do have a source address on there already. It's 127.0.0.1. So let's see what our destination address is. This should be blank. Oh, no, it's not blank, but, okay. I'm surprised that it's not. Okay, I'm surprised that it's not populating those fields with this, like it's not showing up. That surprises me. But I think after you define it custom, it will show up. Okay, so yeah, now we've got it showing up as the destination address. Okay, and it looks like the source automatically went to .14. I'm not sure why that happened. I'm not sure at all why that happened. I didn't even know what subnet mask. I guess maybe it chose the last usable in a subnet, and it assumed it was, well. Oh, and the other thing is, it looks like mine was different than theirs. They came up with 8.14. Mine came up with 1.14. So I'm not sure what's going on there. Because we changed the TTL value, but that's not the subnet mask value, so I'm not sure how it would know. Let's do del a.ttl. There we go. So now if I do a, it doesn't have the TTL value. But we can see it's there. So what we get is if we do IP, we get an IP packet. I wonder if we can do the same thing for like ARP. Yeah. So now we've got an ARP packet, BGP. Oh, so we don't have it for a BGP packet. Because there's no such thing as a BGP packet. What about a TCP packet? Yep, UDP. Yeah, DNS. Yeah, so it's pretty intuitive. You can see, yeah, and it drives home these kinds of concepts too, which are pretty nice. I'm surprised that maybe it's OSPF 3. No, OSPF v3. OSPF. Well, what we can do is do maybe a help. Yeah, so we can do a help, and then do modules. Oh, actually, never mind. They're not modules. So let's exit out of the help menu. Okay, which is Control C. And then we'll do a dir. Oh. Why can't I don't like this interactive. I really don't like this interactive menu that they give you. Because like the help isn't there. Oh, okay, here we go. Oh, okay. Yeah, so now we can see the class. So Skeppy got layers, the iNet, we can get help on that. There we go. So now here's the yeah. Let's see if there's see the help for about layers. See, I'm trying to find BGP, but BGP would just be TCP. So we gotta choose a layer from this list, or choose a content. So is TCP not on the list? It's not. What was I? Oh, iNet. Okay, iNet is on the list. Yeah. Okay. Alright, so let's keep going with the tutorial. We saw how intuitive it was to create a packet. Unfortunately, it's not super easy to see what these are, but if you can think of it, it should align like here ICMP. Let's see if that shows up. There you go. So yeah, it should align very closely to Wireshark. Okay, so this is stacking layers. The / operator has been used as a composition operator between two layers. When doing so, the lower layer can have one or more of its default fields overloaded according to the upper layer. You can still give the value you want. A string can be used as a raw layer. Okay, so let's see how this works. So we've got just a blank IP packet with nothing in it. What we can also do is encapsulate it or wrap it up in a layer. So we're going to wrap it up in TCP. And we can see that in Wireshark here. If I click on a TCP packet, we've got the IP layer here that we saw here. And now we've got the TCP layer there as well. There we go. So we'll see things like fragment and protocol number in this, and the reason we'll see that. So let's see if we've got it here. So yeah, fragment offset 0, and then protocol is going to be TCP, which is, I think that's an 8, it could be a 6, I'm not sure. Let's look at the binary. So 1, 2, 4, 5, 6, yeah, 6, okay. So the reason we have fields here now where we didn't before is because we wrap this up in a TCP layer 4 TCP. So at layer 3, we know a few things. We know what the protocol is. It's TCP, we just told it. And we also know that it's not fragmented. Okay, so we can just keep doing that. Now that we have that, we can also go on the other side and do ether. So ether is a frame header. So there we go. We've got a IPv4 frame header now. We don't have the same type. It looks like it's could be the same type. I'm not sure. But let's see how that compares with Wireshark. So here's the equivalent field in Wireshark. Oh, yeah, so it's the same. It's 0800. Unless that's, I can't read it. Yeah, okay, 0800. Okay. That's type IPv4. Okay, so now what we can do is we can build up a HTTP GET request. There we go. Alright, and then we can build up, now that's interesting, we've got a packet with 2 IP fields, but it looks like it allows you to do that. So I guess this is where you can test how your equipment handles bad packets. You can make a packet that doesn't, that appears to be broken, and although, what's this Pcap? I'm curious about that. I've never seen that. Oh, it's a IP and IP. Yeah. IP and IP encapsulation. Yeah, so you can encapsulate a packet header inside of a packet header. That's what we're seeing there. All right, so we've got one more example to go. Okay, final example. We changed, so here's kind of a broken packet because TCP is protocol number 6. So to say it's going to have a protocol number but not have that be the actual thing that encapsulates it is just I think a broken packet. So that'd be good to test how your devices handle a broken packet. If it's a BGP packet that's broken kind of like this, you should get a notification message back from your device. Each packet can be built or dissected. Note in Python, the underscore is the latest result. So, okay, lower layer, upper layer, default fields, fields overloaded by the upper layer, user set fields. Okay, so, all right. So what we can do is, in addition to just looking at the nice and neat version that they give us, we can just look at the raw bits on the wire. And it's given to us in octets, but it's in hexadecimal octets. Okay, so let's do the underscore. So we'll look at the last. There we go. That's the last packet we created. Okay, let's create a new packet, A. I'm just going to enable the frame header here. And then the next, it's going to be encapsulated with a packet header, IP header. So, and the destination will be www.slash.org. Okay, and then TCP encapsulating, and then it'll be a GET request. Okay, let's do a hex dump. There we go. That looks really familiar. If I go to Wireshark, I change this back to hex. It's the exact same thing we've got there. We've got the Wireshark packet. Now it's not this packet. I could make it that packet, but that'd be great if I could learn how to do that by the end of this tutorial. Just take a hex dump and feed it in somehow. That would be great. Okay, so let's take a look at. Okay, so let's define this the raw version B. Okay, and then we're gonna see, and even though so you can encapsulate a whole series of things you encapsulated, as we've seen here. That is a valid thing. We see that a dissected packet has all its fields filled. That's because I consider that each field has its value imposed by the original string. If this is too verbose, the method hide_defaults will delete every field that has the same value as the default. C.hide defaults. Oh. Okay, so quite a bit smaller now. We don't have the sport or the S port, source port, because that is the default source port. Okay. Reading Pcap files. You can read packets from a Pcap file and write them to a Pcap file. Graphical dumps. You gotta have PyX. Don't have that on this. I don't even have graphics. Generating sets of packets. For the moment, we have only generated one packet. Let's see how to specify sets of packets as easily. Each field of the whole packet, ever layers, can be set. This implicitly defines a set of packets generated using a kind of Cartesian product between all the fields. Alright, yeah, because you can use all the same file for, it's a programming language, so I'm gonna format it a little bit differently than they have it there. There we go. Okay, so now they're using list comprehension, and they're just printing out each element of the list. Okay, so that's each address in /30. .12 all the way up to .15, whether it's a host address, broadcast, or network address, so they'll all get printed. correctly. There, that's correct. Okay. There you go. So now we've got these TTL values, 1, 2, and then 5, 6, 7, 8, 9. So you can kind of see how that works. TTL equals making a list here, and then you can use this tuple to specify a range within that list. Here you use this special net class to or function to generate all of the host addresses within the subnet given. Okay, so moving on. Okay, looks good. Some operations, like building the string from a packet, can't work on sets of packets. In these cases, if you forgot to unroll your set of packets, only the first element of the list you forgot to generate will be used to assemble the packet. Okay, so here's some commands. Oops. Okay, so I don't have these commands. I'm not sure where they think these commands can be entered. They're not clear about that. Yeah, I'm not sure where they're saying that this can be entered. All right, so moving on though. Oh, it almost looks like this is for yeah, this is for a graphical representation, which I can't do in this Docker container here. Sending packets. Now that we know how to manipulate packets, let's see how to send them. The send function will send packets at layer 3. That is to say, it will handle routing and layer 2 for you. The send p function will work at layer 2. It's up to you to choose the right interface and the right link layer protocol. Send and send p will also return sent packet list if return underscore packets equals true is passed as a parameter. Okay, perfect. Sent 1 packets. Oh, sweet. Well, that's cool. I sent a packet. Let's try to Wireshark that. It should have been Wiresharked already. Oh, yeah, because if it's out the, what is this? Is this automatically scroll? Yeah, it is. Okay, well, I'm kind of surprised it's not sending. Maybe it's sending it down the wrong wire. Let's take a look at that. So I'm gonna stop this. And then I'll snip this one and send it. Huh, I don't see it being sent. No, it's not sending for me. Unless this was it? No, because the destination will be 1, 2, 3, 4. I don't think it can send it. It needs to. The ARP table isn't completed. I wonder why this is so laggy like this. All right. Well, let's just keep going with the examples. So next will be send p. So I sent 4 packets. Unfortunately, this Wireshark is crashing on me, so I'm going to close the program. I'm going to stop the capture. Okay, but I will start it again, and we'll see if it works. Oh, and I might need to log off. I'm starting to get tired. It's kind of early to get tired, but I'm getting tired anyway. Okay, so we'll go to Start Wireshark. There we go. Perfect. Okay, well, unfortunately I still don't see anything being sent. Oh, you know what? I'm specifying my interface here, so why don't I just shut this down and then sniff on the links where I'm not having those kinds of issues. Sniff on this link and then specify the correct. Okay, so ETH1 is the interface I'm specifying anyway. So if it's not showing up there, and it's showing an ETH0 instead when I'm specifying ETH1, that's a problem. So, oh, and here we go. They're here. So here's the packet. Here's the custom packet I crafted and I sent myself. So perfect. Excellent. Oh, that's wonderful. Okay. So what did the other one not work? The send. Because I don't know. Maybe because it wasn't a packet? I'm confused. But anyway, the second example there certainly worked. So let's try the third example. Okay, so this sends 16 packets. I guess I'm not sure why it's sending 16, but we can see here's the packets, and it should have. I don't see that data though that was sent in. Yeah, it looks like the data is here, but oh, I see it. So here's the data. I'm traveling on Ethernet. Cool. That's really cool. Yeah, so I can make my own custom message. Let me do that. My own custom message. My own custom message. So here it is, my own custom message. That's cool. All right, so the next example would be to, I guess I'm not sure what this one is. Let's try it. I'm not sure if this one will work because I don't have a capture file here, so they're specifying a path that I don't have. I don't have or at least I don't have the file. I have the path, the temp, but I don't have the file at the path. The Pcap file is how they named it. So yeah, error, no such file or directory. So we'll just skip that one. But it looks like what you can do is save your packets that you want to send in a Pcap file, so you can view them in Wireshark and stuff, and then you can send the whole Wireshark file again over the internet. So you can send the file of packets, which is nice because it's good way to keep them organized and clear about what you're actually doing. Okay, so was there a packet sent for this one? Oh. Okay, well, I don't see that one's being sent. Okay, so we finished all the examples there. The next part of the documentation is fuzzing. The function fuzz is able to change any default value that is not to be calculated, like checksums, by an object whose value is random and whose type is adapted to the field. This enables quickly building fuzzing templates and sending them in a loop. In the following example, the IP layer is normal and the UDP and NTP layers are fuzzed. The UDP checksum will be correct. The UDP destination port will be overloaded by NTP to be 123, and the NTP version will be forced to be 4. The other ports will be randomized. Note, if you use the fuzz method in IP layer, source and destination parameter won't be random. So in order to do that, use rand IP. Okay, so we're going to do this example. And then I think that's going to be it for a while. This is a longer tutorial than I thought. So we're just going to end with this fuzzing example, and that's going to be all I can do for this video. Oops, so we've got no address. Oh, okay. So yeah, let's give it an actual target to go to. Give it 10.10.10.1. Okay, so we're sending packets to that address. I don't see the packets showing up here. So I'm wondering if it's using the right. What's the difference between that doesn't work and this one that did work? Okay, it looks like this one that did work has more information in the here in addition to the destination. It also has the iFace. Why does that not work? Oh, because it's not. It's sendp. Sendp is okay. Well, okay, that was a failure. The problem was that no address associated with hostname. But when I associated an address, when I gave it an address, it did recognize. I unfortunately didn't see anything sent out on the wire, so I'm not sure what's going on with that. But the next video will be injecting bytes here, so I'll save that and include that in the description. So that will be the end of this video. Stay tuned for the next one where I go over the multi-exit discriminator. And if I have some extra time, I continue with this SCAPI demo. So thanks for watching, and see you in the next one.